Welcome to Amplified Education, your exam prep friend. Today we are looking at kinematics, horizontal motion. Please pause the video and try the questions on your own. The question reads, the graph below shows two vehicles initially traveling north. Define the term acceleration. Acceleration is the rate of change of velocity. The second question says you must calculate the value of t on the graph. So here's the value of t. Now at t, you would notice that it is the point of intersection for both graphs. This is where the velocity of both cars is actually the same. You cannot solve that question unless you find the acceleration of car A. You first have to find the acceleration of car A, and to do that, you could use the equation. Let's write it here. The equation VF equals VI plus AT. Now, if you look at from the time from 0 to 8 seconds, you can see that at 8 seconds, the velocity of car A is 0. So we are just going to treat that as the final velocity. So that's 0 equals the initial velocity is 20 plus A, and the total time there would be 8 seconds. And that would give you an acceleration of negative 2.5 meters per second squared, right? And obviously the acceleration is negative because the object is slowing down. Car A is slowing down from 0 to 8 seconds. Then now you know the acceleration of car A between 0 and 8 seconds. What you can then do is that you focus your attention on this particular segment of the motion of car A, only on that segment. And you can see if you focus on that segment that now you could use your final velocity as, because you already have the acceleration, you could use your final velocity as 10 meters per second and still use the same formula to find that particular time. So now VF is equal to VI plus AT. Your final velocity is 10, your initial is still 20, plus the acceleration that you calculated of negative 2.5, and then you make t the subject of the formula. And so t would be equal to 10 minus 20, which is minus 10, and you divide that by minus 2.5, which then gives you 4 seconds. So t on the graph is 4 seconds. Then in 1.3, you are asked to define the displacement, which is a change in position, right? Or a change of position. Okay. Now, the next question says calculate the displacement of car B for the first 10 seconds. You'll notice that car B, all right, in first and foremost, in order to do that, you would need to find the area under the graph. So you need to find the area under the graph, particularly focusing on car B, that's the area. There's a rectangle there, right? And there is a triangle there. So you could find the area, that's 1.4. The displacement x is equal to length times breadth, which would be the area of a rectangle plus a half base times height, which would be the area of the triangle. So if we sub in, the length that is given there is 8 seconds for the rectangle, and the breadth is 10 plus a half. The base for that small triangle would be 10 minus 8, which is 2, and the height is also 10. And so the value of your displacement, when you calculate that, would be 90 meters. And remember, we said that the objects are traveling north initially, and all these graphs, the graphs that are drawn there are above the x-axis, right? The The graphs, well, from 0 to 10 seconds, the graph of car B is above the x-axis, which shows us that it's traveling north, right, in that time. So then your displacement will be 90 meters north. Then 1.5 says describe the motion of car A between 10 seconds and 22 seconds. So between 8 seconds and 22 seconds, car A seems to be now moving in the opposite direction, which is south, but it seems to be speeding up south. All right, we can see that the graph starts from there, 8 seconds to 22, right, seconds, and the velocity is increasing. All right, and always remember that if the graphs are drawn above the x-axis and you were told that they are traveling north initially, it means that whenever the graph is above the x-axis, the objects are traveling north, and below the x-axis are traveling opposite of north, which is south. So since the graph is drawn below the x-axis, that object car A is traveling south. And so there we would say that for 1.5, speeding up south, right? It is definitely speeding up south. But again, secondly, if you were to calculate the gradient of that line, you would get a negative value. And to be quite specific, you'd get negative 2.5 meters per second squared. So if your acceleration is negative, all right, for that segment, then that would mean that if we had chosen at first north as positive, south should be negative. So if our acceleration is negative there between 8 and 22 seconds, then the object is accelerating south. Then 1.6 says we must draw the position versus time sketch graph for the whole journey of car B, right? That is 1.6. All right, so that would be your position, x in meters, and your time in seconds. This would be your x versus time. This is not drawn to scale. Right? This is not drawn to scale. We can see that for the first 8 seconds, the car B is traveling at a constant velocity. And if car B is traveling at a constant velocity, then for your position versus time graph, you draw an increasing, right? An increasing positive gradient graph. So this particular graph, all right, represents a straight line, all right? The gradient of that graph would give you a velocity of 10 meters per second, because the gradient of a position versus time graph gives you velocity. So that's very, very important. Okay, constant velocity is represented by that line, right? Which shows that there is a constant increase of displacement as the object is moving at that constant velocity. Then the object slows down. So to represent that the object is slowing down after those 8 seconds, all right, that is car B. To represent that it's slowing down, all right, it's not only slowing down, the graph is still drawn above the x-axis, which means the object is, traveling north still. Then we would represent that using a set face. Okay, a set face. And one could say, why a set face? We can see that if we draw a set face, the graph is starting from a more steeper gradient to, in fact, we would do it like this. Okay, we would do it like this. Right. So we are starting from a more steeper gradient there of the graph to a less steeper gradient, or to a horizontal line, which shows that the velocity of the object at that particular point was zero, because the gradient of a horizontal line is zero. That's very, very important. You start from a more steep to a more gentle curve, and we would call that obviously a set phase to show that the object is indeed slowing down, right? That would be from 8 seconds to 10 seconds. Then the object then continues now. Well, it speeds up after that momentarily. After the object momentarily stops, it then starts to speed up again, but still speeding up north. So that would look more like this, right? More like a happy face, right? Why a happy face? Because you can see that the graph starts from being obviously there, less steep to more steep. And so the gradient is increasing from that point to that point, which means the velocity is increasing from that point to that point. And if the object is increasing in velocity from that point to that point, and velocity is increasing, therefore the object is accelerating. That's the main point there. That if an object is accelerating, the velocity has to increase, and that is shown by these lines, that you are moving from a less steeper line to a more steeper line. Okay, so that would be how that looks. Let me just remove those lines. Okay. And that would be pretty much how your graph would look. Okay, it would end there, and there, we don't have the time for that part. Okay. Then I'm going to just draw those side by side. I'm going to draw 1.7 here, right? Because 1.7 says you must now draw the distance versus time sketch graph for the whole journey of A. Okay. I hope it's going to fit. I'm going to try and draw it there. And again, distance is d in meters and time is t in seconds. Now remember, position is a vector quantity and distance is a scalar quantity. So we must be very careful in how we draw that particular graph, because when we are looking at distance, we are looking at the total path length traveled by the object. So we can see that A starts off by just slowing down. Okay, it was moving at a velocity of 20 meters per second to a velocity of 0. Okay, this would be the 8th second. And then it starts speeding up south. Okay, if this was a displacement time graph or a position time graph, this particular graph here would actually go back down, because remember now this graph is below the x-axis here, showing that it's traveling south. So the same would apply for displacement. If the object is traveling south or north first, then the graph moves up. But if the object is traveling south, then the graph moves down. But this is a distance, all right, versus time graph. So the opposite happens. The graph doesn't move down, but it continues to move up. And it shows us that the object is speeding up. And so from slowing down to speeding up would have a smiley face. Okay, smiley face there, showing us that it's speeding up from a less steep graph to a more steep graph, showing you that the velocity is increasing. And then obviously we end off there with a constant velocity, or in this case, a constant speed. And so the graph would then increase gradually like that, showing a straight line going up. And obviously the gradient of that line would be represented by this velocity, all right, or by that speed on the graph. And that's how that graph would look, particularly for car A. Then we have the last question there, which is 1.8. It says, after 25 seconds, The driver of car A notices a rabbit initially at rest, a distance of 60 meters away, crossing the 8-meter road at 0.5 meters per second squared. The driver decides to accelerate uniformly at 0.8 meters per second squared for 60 meters. Determine whether the rabbit crosses in time. And so this is not good, what car A is doing. Why would you accelerate if you are seeing a rabbit? Okay, definitely the driver of car A wants this rabbit as a meal. And so what we see though from car A is that we first need to find the velocity of car A, right, between 22 seconds and 25 seconds, because at least there the velocity is constant. We have to find that velocity and then work with that velocity from the 25 seconds that the question is talking about, because we see that after 25 seconds, he decides to speed up. So if we were to continue the path of that graph, we'll draw it like that, because he speeds up now when he is seeing this particular rabbit. Okay, so to do that, remember now, if we want to find the velocity at 22 seconds, we do have the initial velocity and the final velocity for that segment. So we are looking at this point here, that is VI, and this point here, that is VF. So if we have those 2 points, and we also have the time, which is from 8 to 22 seconds, we could use that to find the velocity there. So how would we then do that? We would say that, and remember that the acceleration here of the object and the acceleration under the x-axis is the same, because that's the same straight line. So that minimizes the amount of work we have to do. All right. So we could find that final velocity there at 22 seconds, which is the same as the velocity at 25 seconds. So VF is equal to VI plus AT. The initial velocity is 0 plus the acceleration. Now the acceleration is obviously your 2.5, which we calculated earlier on, and I'm substituting it as positive because the object is speeding up. And then the time, so 22 minus 8, that should be 14. So you substitute the 14, then you get in fact, you can substitute it as negative, because the value that you must get anyway for velocity under the graph is negative. That would give you negative 35 meters per second. So that value there on the graph is negative 35. Once you have that, you can then now calculate the time it takes the rabbit to cross the road if the rabbit started at rest. And you could use the formula x equals VIT plus a half AT squared, not forgetting that the rabbit started at rest, so we don't have to worry about that. We know the length of the road is 8 meters, so 8 is equal to a half. We are given the acceleration of the rabbit here as 0.5. So we can substitute that as 0.5. All right, and then we could find then the time. We make t the substitute of the formula. If we do that, we are going to get 5.66 seconds. So it takes that time for the rabbit to cross the road. All right, so the reason why we're finding that is because we want to calculate the time it takes car A to travel 60 meters if it is accelerating at 0.8 meters per second squared, right? Because the rabbit is here, it's called an R, and it's crossing here. And we want to compare the time it takes the car TA, let's call that TA, the time it takes car A to cover 60 meters, which is where the rabbit is, against the time of the rabbit, the time it takes the rabbit to cross. Now we already have that time as 5.66. Right, now let's calculate the time it takes the vehicle to get to that point. To do that, we could use the formula again, x equals VIT plus a half AT squared. All right, remember the rabbit is 60 meters away. The car is already traveling at what? It's traveling at the initial velocity, we said it's negative what? 35. And we're looking for the time, right? Plus a half. We know the acceleration as given in the question is 0.8 here. Then we're looking for t. So obviously we can change that to a quadratic and use our white calculators to solve for the quadratic and get values of t. When we do that, we should get t is equal to 1.68 seconds, right? Or t is equal to negative 89.18 seconds. Now, we all know that time cannot be negative, so that's not a viable option. So now we have to compare TA and TR. So the time it takes the robot to cross is 5.66 seconds. However, the time it takes the car to reach where the rabbit is 1.68 seconds. And so it takes less time for the car to reach the point where the rabbit is, and it's definitely going to knock it over and cook it for the night. So the rabbit will not cross in time. And that's it. I hope that helps. Thank you.